Question number 6. Which of the following statements is correct with regard to boiling points? Now, boiling points of a compound. Let's say boiling point or melting point. Both have the same criteria. Boiling point or the melting point of a compound depends on the strength of the intermolecular interactions. The strength of the intermolecular interactions. This is important. Intermolecular interactions. Now you should know what are the factors affecting the strength of intermolecular interactions. Now there are 2 points. First one is the amount of intermolecular interactions. How many interactions are there? Amount. Then the type of the intermolecular interactions. Which means whether it's a hydrogen bond, iron dipole, London force, whatever. Depending on the type of the interaction, the strength of the interaction will be governed. So the amount of the interaction depends on several points. These points are: first one, the number of atoms. It's easy to understand. If a species has more atoms, it can form more interactions, therefore the strength of the interaction will be greater. Second one, the number of electrons. The number of electrons, or you can say the molecular weight. If the number of electrons is greater in a species, it has higher number of interactions, which means the intermolecular strength of the intermolecular interaction is greater. The third one is the surface area. If the surface area is greater, it can form lots of interactions with respect to a lesser surface area having species. The type of the interaction depends on 2 things: whether the compound is three things: whether it's a polar species or a non-polar species, or is it an ionic species. Like that. Therefore, let's compare the given answers according to these theory. Right, the first statement, N2 has a higher boiling point than NO. Now let's go to the amount. N2 has 2 atoms, NO has 2 atoms, so we can't compare using this point. Then number of electrons or the molecular weight, they both have the same kind of molecular weight. It's close enough. Nitrogen is 28, NO is it's 14, 16, 30 daltons. So only 2 unit gap is there. It's not a considerable difference. Therefore, there's no use of using the second point. Surface area kind of have the same surface area. So there's no luck using the amount of interactions to compare the boiling points of these 2. Then we have to go for the type of the intermolecular interactions. Now N2 is a non-polar molecule, so it has London forces. NO is a polar molecule. There's a dipole moment here from nitrogen to oxygen. Therefore, it has dipole-dipole interaction. So, London forces are weaker than dipole-dipole interactions. Therefore, NO should have the higher boiling point or greater boiling point. So, the first statement is incorrect. The second statement, pH3 has a higher boiling point than ammonia. This is wrong, because when you consider the type of the interaction, pH3 is a polar molecule. NH3 is also a polar molecule. They look same. Now according to the first point, the amount, when you consider the amount of interactions, they have the same number of atoms. They don't have the same number of electrons, but when you consider the last shell electrons, it's kind of similar. The molecular weight pH3 is greater, therefore pH3 should have the higher boiling point, and surface area is also greater in pH3, so it should have higher boiling point. But the type of the interaction here becomes greater because pH3 has normal dipole-dipole interactions, while NH3 has hydrogen bonds. Therefore, NH3 should have the higher boiling point. It's a practical value actually. If you remember the boiling point curve of the hydrides of group 5th elements, say boiling point, relative molecular mass, it goes like this, decreases like this, increases like this. NH3, PH3, ASH3, SBH3. Now ammonia has a kind of higher boiling point because of the presence of hydrogen bonds. Now SBH3 has a greater boiling point than ammonia because its size is greater and it has a higher molecular weight. Therefore, the second statement is also wrong. It's because hydrogen bonds are relatively much stronger than normal dipole-dipole interactions. Third one, xenon has a higher boiling point than krypton. Now, if you look at the noble gas series, helium, neon, argon, krypton and xenon. Down the group, their size gets increased because of the number of shells getting increased. Therefore, the number of electrons getting increased, the molecular weight getting increased. All of them contain London forces. The number of London forces that can be formed by each atom will increase down the group because the number of electrons are increased, or the molecular weight increases, or the surface area increases. You can use any point. Therefore, xenon has a higher boiling point. Yes, that is true. So the answer for the sixth question will be third one. But let's compare the other ones as well. Fourth one, ethanol has a higher boiling point than propanol. Now both of them contain OH groups. That means their major intermolecular interaction will be hydrogen bonds, and both of them have R groups. But the size of the R group is bigger in propanol. In this compound, the R group is bigger. Therefore, it can form more London forces. That means it should have the higher boiling point. Therefore, ethanol has a higher boiling point statement is incorrect. So that statement is wrong. This one is the answer. Fifth statement, this compound has a higher boiling point than this one. So this is isopropane, this is butane. Now both of them have the same number of atoms, same number of electrons, same molecular weight, but their surface area is different, and they have the same type of interaction. Since they are alkanes, they form London forces. Now this is a branch molecule, this is a long chain molecule. Now the long chain molecules have greater surface area than branch molecules. Therefore, long chain ones can form lots of London forces with respect to branch ones having the same molecular weights, and they can be easily packed and closely packed. Therefore, they can form more strong London forces. Now these cannot be packed like that. Let me show you that. Let's compare 2, 3, 4. This is the long chain hydrocarbon. This is the same hydrocarbon but with branching. Now if we try to arrange them or pack them, these two can be packed very closely to each other. Now if you consider this one, they cannot be closely packed like that. See? So if we draw the London forces, here the London force is shorter and it can form lots of London forces. Here the London force is longer, therefore it's weaker, and only few London forces are formed. Therefore linear or the long chain hydrocarbons, this is long chain, or you can say linear. Linear hydrocarbons will have higher melting points or boiling points with respect to branched ones. Therefore, fifth statement is also incorrect. This is also wrong. So the answer for the sixth question will be the third answer. Let's go to the next question.